I will try not to delay you for lunch too long. Before we get started, I wanted to thank the organizers of this conference. It's a lot of work to put these on. So make sure you reach out to them, the Red Badgers, the volunteers. Give them a big round of thanks. I personally appreciate that they have not black T-shirts. Thank you for that. And a single track conference, because you're here, you're obligated to pretty much. So I'm going to talk about hiding neural networks hiding shellcode inside of neural networks. I've been calling this project the ENNEoS, the Evolutionary Neural Network Encoder of Shenanigans, because it really annoys my marketing department. So who am I? I'm a senior security consultant. I do pen testing for external clients. We're a consulting firm based out of Ohio. I'm a computer geek. I'm old. I've done lots of things. The agenda, in case you want to decide to bail now, I'm going to talk a little bit about shellcode for those of you who aren't really on the offensive side. And then I'm going to talk about neural networks, why it's an interesting technical approach to this problem. We're going to talk about the encoder a little bit. And then I kind of want to give you a glimpse under the hood. I'm not going to lie to you that the actual encoder is incredibly complex. Uses a lot of machine learning techniques. You actually don't have to understand any of that to use this software. Although it's a proof of concept, it's not a tool yet. But I do want to give you a peek. You can totally take a nap at this point. I'll warn you when you can space out. There is a concept, though, called fitness functions, which are conceptually really, really easy to understand. A little hard to implement, but they're very easy. If you were going to pick up this code and try to use this, that's what you would have to get. So I'm going to cover that a little bit more. We'll do the loader, which is really basic, that actually executes you and pops the shell for you. We'll have a live demo, which will fail because I don't have backup videos like all the intelligent presenters before me, and a chance to ask questions and throw clever insults my way. So shellcode, it's a really small bit of computer instructions. This is often we call it shellcode because we'll run this in a box that we get kind of a way to execute code on, and it'll give us an interactive shell. So that's typically what we're doing with it. As a pen tester, I'm not going to have time to write custom shellcode for an engagement. I'm going to use pre-made shellcodes or tools that are going to create it for me. Now, the antivirus vendors and the incident response and reverse engineers know about these tools well, and they make signatures for them. So if we're going to use the easy stuff, the tools that generate it for us, we're going to need to kind of obfuscate it in some way. There's a lot of tools that will do this for you. Unicorn, that my company does, works on. Ebola, there's a bunch of ways of doing this. You can encrypt it and hide it until you decrypt it in memory. That's effective. You can change the shellcode just a little bit, not change the actual logic of the code, but just change it so it breaks the signature. And of course, today I'm talking about hiding it in a neural network. So why would I want to use neural networks for obfuscation? So neural networks are kind of interesting. They're inherently a black box. They're basically incomprehensible to humans and a lot of our tools, which is kind of funny because a neural network is basically a simulated brain at a very small scale. But the creation of neural networks by computer scientists way back in the day was based on studying how our brains work. And it's basically a model of that. And interestingly enough, a lot of the attributes of brains come along with the ride. They're great for computer vision. They're great for pattern recognition. We can't create algorithms that do this nearly as well as a neural network. But we also can't really tell you what's going on inside of it. It's literally a black box. And there's a couple of interesting types of neural networks. And what I'm going to talk about today is a technique that can create something called a recurrent neural network. Now, if you think of a neural network, it's a small brain, and I'm going to put in some kind of input. And let's say it's a password. If the password's right, it's going to drop my payload. If it's wrong, it's going to do something else. A recurrent neural network has the ability to form memory, which is really unique in neural network techniques. And what that means is that I could actually train one to only output my payload after a correct sequence of inputs, because it could remember what the previous input was. So that's one ability that this kind of approach could potentially have, is that ability to form memory and have much more complex triggering mechanisms to drop your payload. And then, of course, neural networks are great for storing data like shellcode, right? They're actually not. This is actually a really stupid application of neural networks. To be honest with you, this is not what they're good at. I'm really using them because they're so hard to understand. They're perfect obfuscation machines, which is usually a problem. Like if I'm an engineer and I'm trying to pitch the use of a neural network in like a safety critical application, trust me, I've tried this. It's hard because people say, well, what is it going to do in all these situations? Beats me. Let's find out. That's not really reassuring to the QA team, especially when you have recurrent neural networks, because you really can't brute force all the possible things that it could do. We just don't have a good way of figuring that out. This is kind of a PhD level problem. There's interesting research trying to figure out ways of doing this, but we're not there. And I don't know if we're going to get there anytime soon. So I made the ENNEoS encoder, and what it does is it uses genetic algorithms to solve the problem. So I'm not designing a neural network and training it. I'm creating an evolutionary system that's going to evolve the neural network for me. That's hard. I'm not be honest with you. But the reason why is because it can do complex things like create recurrent neural networks, which is not a common sort of solution. And then I do have a really simple loader just to test it out, to show that I can get that shellcode back out, pop a shell, do your happy shell dance, all the fun stuff. So I mentioned earlier that there was going to be the peek under the hood, and you could just totally space out and go in Twitter, and we're at that point. You can completely space out right now. So this is what's going on in the underlying classes of it that's abstracted away that you don't really have to understand. Any Python coders in here? All right. This is written in C++, so I'm really sorry. We'll talk about Python later, but I'm really, really sorry in advance. But really, the complex stuff is really abstracted away for you. So this is using a technique called Neuro evolution of augmenting topologies. I'm not the only computer scientist who's really bad at names, okay? Which is called NEAT. And this was created by Dr. Kenneth Stanley at University of Central Florida a couple years ago. I spent many years of my life digging into this in grad school. A lot of this software was written, but my classes for this, my implementation was from grad school that I've repurposed. And it does a couple of neat things. I want to give you a quick little tour of a neural network. Let's see here. Is this working? Yeah. Okay, so this is a really basic neural network and example of my terrible OpenGL programming skills. So this is a visualization, and what you have here is these green circles are neurons. These are also neurons, these light blue ones, and these are also neurons. So this is the input layer. So as an example, this would be where we'd be passing our passphrase, our password. And up here would be where the characters of our shellcode would be popping out in this particular example. Now, if you think about a neural network as a virtual machine, what I want you to look at this as is those neurons and the links between them are the hardware of that virtual machine. In those links and in those neurons, there are activation responses like weights, like floating point numbers, and weights on those links. Those numbers, those values, that's the software of that virtual machine. Now, this is a completely different architecture than what you've got in your pocket, that your laptop is using. This is very different. We're all using something called a traditional von Neumann architecture. You've got a CPU and you got your memory bank and your I/O and storage. This is very different. The hardware, the software is distributed throughout. So if I had two shellcodes in here and a reverse engineer was looking at it, they're not going to see the right side executing when it's dropping one shellcode and the left side. The whole thing's executing all the time. This is going to be a real pain in the ass for reverse engineers. If there's reverse engineers in here, when this is ready, I'm going to owe you a beer. I'll prepay it this weekend and I'll buy you a beer now. So it's really, really cool kind of architecture. And again, formed on us, we're too dumb to understand our own computer architecture that's in our heads, which is kind of funny. So this neat algorithm, it's not only going to evolve the weights, the software, it's going to evolve the architecture too, which is kind of a nice approach why I like to use it. So it will evolve those additional neurons that's in between, in the middle there, and all those links. So it's a really neat solution or technique. And what you see here is these dashed lines. Hold on. Oops, sorry. Oop. Wrong button. I can't computer. These dashed lines are the recurrent links. That's literally a loop back in the neural network. So the flow of this is if I have my inputs down here and each one of these input neurons is a character of my password, When I push those in, then I'm going to execute the neural network, and it's going to be pushed up through that neural network, through all the links to the next round, the next layer of neurons, and on. And each link it goes through is going to be adjusted based on the weight of that link. It's going to get to the next neuron, and based on the amount of signal coming across its virtual synapse, if it bypasses its activation response, it'll fire on to the next level of neurons, kind of like the brain does. That recurrent link is actually going to let loop back so that something's going to be left over. If you have a traditional neural network that doesn't have those recurrent links, after it finishes executing, it's back to its base state. The next time you throw something in it, it's not going to be influenced by any shape or form what came before it because there's nothing left over. But with those recurrent links, there's a physical mechanism that it can leave something behind, and that allows it to form memory. So you could train it to say, only drop my payload if I enter this data, followed by this data, followed by this data. And this is going to make brute forcing it really hard. One other incredibly dorky thing about this, if you're not already dorked out enough, is that the NEAT technique has a valid crossover operation. So I've talked about it's a genetic algorithm, I've talked about neural networks, but the system doesn't actually work on neural networks. It works on DNA. So there's a genome for all these neural networks, and that's what the genetic algorithm works on. Now, there's enough data in that DNA to create the neural networks. But the fundamental unit is that DNA, and there's genes for neurons and links and the weights, the software, the hardware, and we'll see it a little bit later. But the neuroevolution of augmenting topologies actually has a crossover operation where it can take two strings of DNA, perform the operation, and come up with a new string of DNA that meaningfully inherits attributes for the two contributing strings of DNA. And if you take that out of computer scientist speak, what we're talking about is reproduction. It can make babies that actually have attributes of the two parents, which is really, really unique in this field called neuroevolution. And really is a very powerful mechanism for making that evolutionary process that we're simulating work better. It can solve much more complex problems. Okay, so everybody can wake up, everyone. This is the part you'd actually have to get. We're back up at a higher level. So the genetic algorithm is actually going to solve the problem for you. You don't have to figure out how to design a neural network or what weights or neurons to put in it. The genetic algorithm will do that for you, but you have to provide it some guidance. And that's what a fitness function is. So if you think back to Darwin's theory of evolution, I can't remember who actually penned the phrase survival of the fittest. If you're going to go grab this code and you're going to run it, it's your evolutionary process. You have to define what is fittest. So that's what kind of is fun about genetic algorithms, is because you can do all sorts of fun experiments as to, if I drove evolution with this concept instead of that concept, you can come up with some pretty neat solutions. But here, we want to basically drive it to create neural networks that output the shellcode when we want it. And it's literally just a scoring algorithm. That's it. Fitness function is literally just take a neural network, look at what I gave it as an input, look at what it output, and give that a grade based on how close that is to the behavior I want. That's it. That's all it is. Of course, it's a little trickier than implementing it. We'll talk a little bit about that later, but if you can provide that score, and the genetic algorithm have a large population, because evolution doesn't work with one or two individuals. It needs lots of folks to work. And you're going to give it a grade for all those in the populations. Over time, it's going to be able to identify the ones that are performing better. They will be able to reproduce more. More copies of it will be made, more mutations of it will be made. The ones that perform poorly over time will die out. Very simple stuff. Simulate that in mass over time, and it's going to slowly find its way towards your solution. So the fun thing is that will actually solve this for you. Now, you could sit down and just write an obfuscation system yourself, probably take a couple weeks, or you can create an evolutionary process that'll solve it for you and spend 6 months doing code, like I did. I'm not a good software engineer. I'm a fun computer scientist. But if you think it's fun that the genetic algorithm will solve this for you, I agree. I think it's really, really fun. So the problem, of course, is while the fitness function concept is really simple, it's really hard to pull off in practice, because You'll make one, you're going to run it for a long time, you're going to see what pops out at the end when you get your solution, you're going to test it, and you're going to be like, that's not what I was expecting. And then you look back at your fitness function, like, well, shit, of course that's what I ended up doing. It's the lather, hair, rinse, repeat, and it makes sense in hindsight when you see it, like, of course that's what I ended up with. So there's a lot of tweaking and retrying, and unfortunately this takes a while to run when you're doing complicated things. So it's still a work in progress, for sure. So let's talk about what I do have currently in the proof of concept is for fitness functions. The first one, which I'm demoing today, was really just to answer the question, can I actually evolve a neural network with shellcode in it and output it and run it and pop my shell? That's literally all my first step fitness function does. And the fitness function doesn't care what the input is. All it's looking for is it outputting the correct shellcode. I do have a second one that's a little bit more practical in that it's got, I call it the double stuffed Oreo. It's got two shellcodes in it. One is literally a NOP sled. If the password is wrong, it outputs a NOP sled, which is not malicious. It just skips to the next instruction. It doesn't pop a shell. It doesn't do anything malicious. It's kind of stupid, but that's what it's going to do if the password's wrong. If it's right, it drops some interpreter shell and pops your shell. It drops the real malicious one. That one seems to be working, but it appears it's going to take about 2 to 3 weeks to encode on my laptop. So that one is not ready for prime time, and I've got a lot of performance issues to solve. But my first one is working, and we can get the shellcode back out. I don't have the backup video, so it'll probably fail on me, but we'll see. The encoder, what it's going to do, I mentioned that you have to have a large population. Right now, I've got it configured for 3,000, the population size. And what it's going to do is it's actually going to chunk the shellcode, because what I found as I started writing all this is that I couldn't create one giant neural network that held the shellcode. It was just, the encoding time was exponential. But I could break it into smaller chunks. So literally it takes, I've got 500 bytes of my shellcode. I'll take a couple of characters at a time, break it off, and make a neural network for the first 2 bytes and another neural network for the second 2 bytes, and on and on. And that works a lot better. So instead of one horrific neural network to try to reverse engineer, someone would have maybe 500, all with slightly different architecture because they were evolved differently. So that's still kind of a pain in the ass. So it's going to create, the bots are a wrapper around the neural network. So neural networks take floating point inputs and outputs between 0 and 1, which is really inconvenient for a lot of use cases. So the bot wrapper literally just translates like passphrase, strings back into the 0 and 1 inputs it needs, takes the output, converts it back into the bytes I need for shellcode. So it's just a wrapper. And it gets 3,000 neural networks from the genetic algorithm and schedules the jobs to be run. I've got a bunch of execution threads that are going to grab those, so a couple of folks out of the population to test. It's going to stimulate them with some input. It's going to record the output. And then it's going to run it through that fitness function and get a grade for that particular neural network. At the end of it, when all the 3,000 bots have been tested, the main thread just takes those scores. First, it looks for a solution. Did I actually solve the problem? And if it didn't, which it usually doesn't, it's going to put it into the genetic algorithm and call evolution. So all the neural networks are deleted. Their genomes are mutated. There's babies made. The weak ones, after a couple of generations, die off. All this fun stuff. A lot of mechanisms under the hood. And then a new generation is created, and you start the cycle over again. And you keep doing this over and over until a solution is found. And it slowly kind of gets closer and closer to finding what the solution might be. The loader is much simpler. The encoder is going to, when it finds a solution for a particular chunk of the shellcode, it's going to save the DNA, the genome, to a file. The loader simply just reads in those files. It's going to recreate all those neural networks from the DNA. It's going to stimulate them. It's going to put them in the bot wrapper so it can use passphrases a little bit easier. It's going to push the inputs in the bot. It's going to take the output from the neural networks, and it's going to copy it into executable memory and call it. And then you get your shell. So let's watch a demo fail, shall we? So to start this off, sorry, we need shellcode. So we're going to create, let's see here. Oh, what did that? Hold on. There we go. So we're on a Kali box. We need some shellcode that we're going to encode. We're going to use Metasploit, MSF Venom, and we're going to create shellcode for a Windows box, just complete vanilla interpreter shell that's pointing back to this particular VM. Okay, so this Kali box will be our command and control for this shellcode. And we're going to go ahead and create that. We're dumping this out as raw shellcode, just the raw binary. And there we go. And what I'm going to do is I'm going to convert this into a C array that I can include into source code. I've got this little script that does that. It also will encrypt it if you want to make custom loaders. This is all on my GitHub if you want it. Hey. I love Python for little things, you know? For big things that have to go fast. I'm a crusty old Unix guy. I literally shaved the beard off this morning. No. Don't I look nice? Huh? No. My wife would be impressed. Okay, so we've converted this binary file into this header file. And let me just show you this real quick. It's not encrypted, but this little Python script, yes, it's Python. Tough crowd. We'll encrypt it for you if you want to use this for writing more traditional. Let me just blow this up. Oop. So this is literally that shellcode that was just generated. It's 439 bytes. So we're going to take this and we're going to copy this source code off to the my encoder directory. Dev ENNEoS. Encoder. If I told it what? I really hate Mac keyboards. I know. I'm missing a lot. Okay, so we should be over there. Let's jump over and do some encoding. Now, the ENNEoS encoder crashes on Kali. I have no idea why. I haven't looked. I don't do dev work on Kali. So I haven't looked into it. So I'm going to do the encoding on Debian. But we should have should be our file that we just brought over. Is that okay? 439, was that correct? Okay. So this is our shellcode. This header file is included in the encoder. So what we're going to do is make sure this is empty. We're going to build it. For those Python developers, this is called a compiler. It catches a lot of your bugs before you run the code. I think it's like spell check. Okay, so we've built our encoder, and I'm going to go ahead and start this. It's going to be a little messy, like my code, but we're going to go ahead and start encoding this. And what you're going to see, once it settles down a little bit, you're going to see it's chunked the shellcode. There's 439 chunks, so we're doing one neural network per character of the shellcode. That runs really fast. Great for testing. And let me just go ahead and kill this so we can kind of focus on it a little bit. So let me scroll up to one that we got a solution to. Here's 11. Okay. Yep, solution found. So the 11th character of the shellcode, it took 10 generations to solve. Solution found. And then, so it's going to go through all these, and one at a time it's going to solve for that particular chunk, and then save that file off. It would take me about 10 to 20 minutes, even with that really basic fitness function of just can it output the right shellcode. So I'm not going to make you sit through that. That's time better spent like looking for parking or something, like, you know, too soon? Okay. I've got one pre-saved, but I do want to show you what it's actually outputting. So there's like an index file that the loader will read, so it knows all the different chunks and where the individual DNA strands are in the separate files. These are all very basic, just a couple of neurons. They're not too complex yet. But let's look at, let's take a look at what one of these DNA look like. So you can kind of get an idea. Let me break this down a little bit so it's easier to look at. This is some high-level information about the neural network, and then we start getting into the individual components. Let me see if I can get down to this neuron is an output neuron. This is the output neuron that actually outputs the character. It is the fifth one, and we'll see there's a lot of stuff in here. Let me just break this up. So this is an output neuron, and we see it's got an activation response. This is going to determine, based on the synapses, the links coming into it, depending on how much signal it gets, if it exceeds this threshold, it will fire on something. The links inside of it, you see this is a link from neuron index 0 to this one, 5, and that link, that synapse, has a weight. These weights and activation function, that's the software, if you're thinking about this as a virtual machine. The neuron itself, these links, that's the hardware. So this is that specification. This is literally the DNA data that the genetic algorithm works on, and it gives you enough information to create that neural network. But since I'm too lazy to do all that right now, what I'm going to do is copy a pre-made one. And you see I've got quite a few chunks in this one, but it solved the entire thing. One thing I like to do is when I do this for a future, go ahead and copy that encoded output into it, because if you don't, you're going to forget what it is, and you're not going to be able to reverse engineer it back out unless you run it and throw up Wireshark to see where it's calling off to. I've made that mistake. But this one is, this is an old one. Let's reload it. This one's actually a different size. So you run MSF Venom these days, it's going to generate a little bit differently each time. So this one happened to be slightly smaller. So the shellcode's a little bit different, but I actually copied the command into a comment. It's literally the exact same command I ran before. It's same IP address and everything. So now that we've got the an encoded shellcode in neural network form, we want to create the loader that will execute on Windows. So because I'm schizophrenic and I don't have a good workflow, all my cross-compiling tools are in Kali, because that's where I use them. So we're going to go back to Kali. And I want to show you the loader. It's really basic. You see that? So right away, it's going to look up into that same directory we were just at to look for those that index file that's going to point it to all the individual kind of DNA strands for the genomes of the DNA. And let's get down to the fun stuff. Okay. So it's basically a big loop for all those genome files, but it's got the DNA, the neural network brain, and the bot wrapper. That's going to make it easier to use. And it's literally just going to read the DNA in from the file. It's going to create the neural network. So phenotype is another word for neural network. It's going to create the neural network for the DNA, and it's going to insert it in that bot. It's going to push in our passphrase. And again, this is that first step proof of concept, so it doesn't really care what the input is. It just needs an input. It's going to call update, which is basically run the neural network, flush everything out. And it's going to get a copy of the brain's outputs. And then it's going to kind of push them onto a vector, like an array, just kind of save them up until it finishes looping through them all. And let's see. At the end, once it has them all, by the way, this is not stealthy at all. Like, this is not meant to bypass things. This is just to demonstrate it running. It's going to allocate some executable memory, copy that shellcode back in, and then call it. That's all it's going to do. So, and because I'm too lazy to make this nice and clean. I just wrote a cheating script. It's not in Python. And it's just going to cross-compile it for Windows. And there we have our Windows executable. So in theory, demo gods, when we run this in a Windows box, it's going to call back to our Kali box and we get a shell. But first we need our C2. So this is Metasploit. We're using Meterpreter, which is a Metasploit payload. We're going to set up our handler to be listening for the callback from the Windows box. It's configured with the same Windows Meterpreter reverse HTTP, very vanilla, very basic payload. This is our localhost IP for the Kali box, and we're just going to go ahead and run that. And we can see that it's running, and we'll run over to everyone's favorite victim, Windows. Okay, so there's our executable. We're just in a shared directory between the VMs. So in theory, we run this, we should get a shell. Now, this is going to happen fast, so I'm going to kind of walk through the print statements that are in the loader, just so you kind of know what's going on. First, it's going to read in that shellcode chunk data index file. So you'll see it like listing out all the indices of the genomes of the different chunks. And then you'll see it looping through all the different neural networks. So you'll start seeing it print out the shellcode characters. So after you see all that, then it'll actually copy it into memory and execute it. Assuming I remember to turn off Defender. Defender has actually picked up a signature for my loader because I wasn't very good at not getting that submitted. My OPSOC was bad. And because it doesn't take much to stimulate it and get a Meterpreter payload to drop out of it, they actually, after a couple of weeks, they picked up a signature for it. So thanks for that, Microsoft. So it's reading in our DNA, those shellcode outputs, and it's running. Hopefully it worked. Hey, and we get a session. All right, Windows. Drop down to a shell. Thank you, demo gods. So now I'll probably feel at like working PowerPoint. Okay, so where does the project stand? This is a really tough researchy project. It is definitely not in the practical stages yet. I started off thinking, hey, I bet you I could do this in 3 or 4 weeks and figure this out. That was about 6-7 months ago. But I have proven my first question was, can I actually do this? Can I actually get shellcode into a neural network and back out again using this really complex approach? There's a lot easier ways of doing neural networks than this that are probably a lot computationally faster. But I kind of want to see if I can get that recurrent link because I like the idea of having a sequence of inputs. It doesn't have to be a passphrase. Maybe it's the domain it's joined to, followed by the host name, followed by the Windows version, and just kind of randomly throw these in. And if everything just lines up so, it drops the right payload. I like that idea, and I'm going to keep working in that direction as long as I think I'm making progress. Next, I need to make it practical. I think I've got a practical fitness function written that will output benign shellcode if the password's wrong, but again, it's going to take 2 to 3 weeks to encode. I've got a lot of performance code debt that I have to pay now, and I'm kind of working on that. I'm kind of splitting my time between working on fixing the multi-threading and on a private branch where I'm making CTF challenges for reverse engineering. Couple of conferences coming up that need CTF challenges, so I'm going to try to make some progress there. But next, I need to make this practical. A lot of that is make it significantly faster. And then it's really not easy right now. You're compiling C code. If I wanted to make this easy, I think you need to be able to include the shellcode. Basically, you don't need to recompile C to make this work. That's ridiculous. It's fine for testing, but I need to solve that if I want to make this easy. If I want to make a tool that's really easy to use, I kind of want to get some feedback from reverse engineers first before I do that. in case it's really, really impossible. Maybe I don't make it easy. My immediate to-do list is to finish off my CTF challenges branch, try to get something useful out of it, and start getting this in front of reverse engineers to see what they think, see what this looks like when it's blown up in IDA Pro. The performance improvements, it's right now, the multi-threading is based on the assumption that it was going to be one giant neural network, which is not where I landed. I landed on the chunking. That is actually going to scale much, much better because I can actually create their independent chunks. They evolve the same control logic as to what to drop when, but its output is different. So I could actually create a completely separate evolutionary process for each one, and that scales perfectly. There's very little inter-process communication with that. So I've started working on that refactor. That will make it scale much better. I could go grab a 32-core droplet in DigitalOcean and blow through the stuff pretty quick. Right now that doesn't work because it just doesn't scale very well. The code cleanup. Now those underlying classes are really clean because I haven't had to touch them. When I said that's abstracted away and you don't have to fiddle with it, I mean it. I haven't touched that code in months. Haven't had to. The encoder code, though, however, is quite a disaster because I kept going this direction and then redirect this way, and it's a mess. I won't lie to you. It's up there on my GitHub. Trust me. You can go look at it and laugh at me. I'd like to implement some more advanced fitness functions. I've got the second one that just isn't practical encoding-wise. I'd like a third one that drops, if the password's wrong, it drops something benign, like a hello world. If you drop an easy-ish to guess password, it drops some payload, but isn't the real payload. Maybe it points at his C2, not my C2. And then a sequence of inputs that drops the real payload. I'd like to see that work. This is going to take a lot of work. And there are a couple of use cases that I could see being plausible. So maybe I can make some pre-baked fitness functions. And for you Python folks, it would be really nice if I could bind off to Python. So if one of the pre-baked fitness functions didn't fit what you needed to do, you could write your fitness function in Python. That's not where the computation is being spent. So there's no reason to do that in something fast and elegant and timelessly aged like C++. So, yeah, that's pretty much it. Those are my plans. My wife would disagree with this to-do list, but that's my plan. If you want to contact me, if anyone wants to try this out, that's my work email. You can find me on Twitter, Slacks, NetSiteFocus at Hoodooer. That's the GitHub where it's at. Please, grab it. If you want to try it out, don't hesitate to contact me if you're having problems. I have problems with it too, so I feel your pain. And if you're a reverse engineer, you want to dig into this, I'd be happy to give you some samples. I don't think any reverse engineer should torture themselves getting this to work just to see what this looks like under the microscope. So I'd be happy to help folks with that. And with that, insults, questions, comments? Yes, sir.
So did you, when you were generating some of those first shellcode binaries, did you have any cases where it crashed the VM?
Oh, yes. Well, not the VM, but it would crash. One of the tricks with a fitness function is that it's got to be continuous. Like if I have one neural network that performs just a gnat's hair better than another one, it's got to get a better score. It can't be like an A, B. Oh, it's in a range, so give it a B. It's going to stall. Your whole evolutionary process, if it works, it's going to come up with these like just on the edge, and with the size of these floating point numbers, sometimes there'll be a little bit of variability, and it may output a slightly different character, and you get a crash. So it's really all about making sure you have that continuous gradient of scores. You really never want to have, unless two neural networks performed exactly the same way, they should not have two exact scores.
Have you seen that happen in the work you were doing here?
Where they come out with the exact same output?
Yeah.
Probably. I see it where it's these solutions found multiple times. It's possible that two came out with exactly the same, because it's taking that output that's a floating point number, but it needs to map it back to a hex value of the shellcode. So if it's in the range, the wrapper bot will say, oh, that's a NOx90 or something. So they could be slightly different, but their actual behavior is the same, but the scoring is based on the floating point numbers. So it's unlikely, but it's possible. So at the end of the day, the scoring is different than what you want it to do. which is kind of interesting because I've done experiments where you weren't actually driving evolution based on the objective performance of the neural networks. You're actually grading them on the novelty of their behavior, because for some problems that's actually going to work better. But at the end of the day, I care about the objective performance, right? So the check for did I solve it? It's not checking for how novel was its behavior. The check is, did it solve the damn problem, right? But evolution may have been driven by some other metric. This problem is very simple. It's hard to pull off, but it's conceptually simple. Objective performance, how close is a perfectly fine and adequate way to approach it. So, but yeah, you always want to check to say, what did it end up doing? Because that's what you're going to execute. Yes, sir. So the neural networks themselves don't take very long to execute. It's the fact that I have like thousands and thousands of them over generations and generations. The neat technique is really good. It starts minimally and slowly grows the neural network. So it actually ends up usually with pretty tight neural networks. They still end up pretty complicated, especially when you get the recurrent stuff. I think it's more if you're looking at like maybe a traditional like backpropagation technique. I think would actually, if you use just traditional neural networks, feed forward, back, I think this would probably be really fast. It's a pretty simple problem. I haven't tried it yet, but that's kind of my plan B. If I can't get to the functionality I want, I might step back to a more traditional technique and just forego the sequence of inputs trigger. Probably make something practical pretty easy, but probably a lot faster too. Yes.
How are you validating against false positives?
Against false positives?
Yeah. Password A, password B gives you the same result. Password C gives you
Well, this first one doesn't. It doesn't. The fitness function doesn't grade any differently based on the input. So I have no expectations with the first proof of concept that it's going to do anything differently. So yeah. So you could have a very robust fitness function that's going to have a huge password list. And if it's not the right password, that's going to be computationally ineffective. The one I have now, you can figure how many loops you want to do, and it'll randomly generate a password that's not right, and it'll have the right one. And it does kind of not correct password stimulants and correct passwords, measures them both, and it's looking for, if it's the wrong password, it's outputting an obsled. If it's the right output, but you would at the end need to do very thorough brute forcing. I suspect that it's probably going to be for those first fitness functions where you're trying to go very fast, where you're not doing a lot of stimulants, that you're going to find that if you get close to the password, it's probably going to dump the right shellcode. Right. So I think that's going to take a lot of brute force testing, because at the end of the day, I think reverse engineers are only really going to be able to approach this from a brute forcing perspective. So that's going to be critical. But I got to get it to practical before I can get to the brute forcing to really test that out. But yes, I think absolutely 100%. I suspect once I have a working but very cheap fitness function that's not doing too many loops, because I'm trying to go fast and test, that I'm going to have that problem that if you got pretty close to the password, that it's going to dump the right shellcode or my payload that I don't want dumped. So, and then you'll have to refine and make it more stringent. But right now I'm still in a little bit of an exploratory phase. Yes, and I think that problem would be easier to approach from the more traditional like feed forward back propagation, because there's so fewer computations that I could really train the snot out of it, to be honest with you. I could really slam it home. So I think that plan B is starting to pop up in my background, and I've done those before, and I've got a lot of software written for that. But I still want to kind of keep going this route a little while longer. I haven't given up yet. So, doing okay in time? Anyone else? Yes, sir. No, I'm not. This is all CPU bound because I'm old and I'm lazy. I'm just lazy. Well, I'm old too. It's just it's easy to. I wrote this for grad school, and I had access to 48 CPU core clusters all to myself, so I didn't need to. I've not aware of an implementation of Neuro evolution of augmenting topologies that uses GPUs. Now, this is my own implementation, but it's based on reading the algorithms and papers and stuff. If I go to another technique, a more traditional technique, I probably could find something that's like OpenCL based, really speed this up. I'm not aware of a Neuro evolution of augmenting topologies implementation in OpenCL. That would be amazing. So. Yes. Once I finish the refactor, it will scale exceptionally well to more cores, but it's still CPU cores. So, but DigitalOcean droplets are cheap, so I should be able to make this significantly faster than it is now. Anyone else? Yes, sir.
So for kind of the long term, after you have a good idea of where you are with fitness functions you have, are there other kind of more meta fitness functions that like creating its YAML rules or
I keep using passphrases and sequences because it's easy to communicate. I don't do red teaming for TrustedSec. I'm more in the apps section, so I'm not really doing stuff like that. But I could easily see, instead of looking at necessarily the right password, maybe it's the conditions are right. If you had, completely, you're deploying this in a network where you have no connectivity to an outside server where you could load something else, and you have to package all your payloads into one binary. You could put in multiple payloads in here, and the control logic could be more along the lines of, are the conditions right for that payload? Domain, joined, host name, things along those lines. The use cases for that are getting a little bit slimmer. But I think that could be really interesting to get away from passphrases and look more at environment. Is it the right domain? Is the right host name? The right version? Does USB devices have a history? Am I sandboxed? Is there any cache on the browser? Trying to make sure you're in the right place.
So I'm thinking more on the actual output shellcode. Does it match signatures? In which case it's not fit or
It's not creating the shellcode. It's just holding the shellcode. We're treating it as a USB device. It's not creating its own shellcode. Yeah, it's taking the shellcode itself, the payload, and it's taking the control logic and putting those into the neural network. The nice thing is, above and beyond just encrypting and decrypting in memory, is a reverse engineer wouldn't necessarily know how many payloads are in there. And the control logic for what to drop when is also in the neural network. That's kind of what makes it hard to pull this off. But that's kind of a nice thing. Now, you could make this a lot easier by just having a couple of payloads encrypted, have your control logic and the decryption keys in the neural network, but then the reverse engineer is going to know how many payloads there are, and they're going to know to keep digging. If you put the shellcode in there itself, they won't necessarily know to keep digging. And that's kind of mean. That's why I'm kind of going for like the hard way first, because I want to get there. Yes, sir.
So with the shellcode, I just thinking about you could go ahead and target a non-Windows platform like a Linux platform or something as well. But would it still work the same without having to change anything about your process?
You'd have to change the loader. Yeah, how it.
I mean, in terms of the neural network part, no, that wouldn't change, right?
Nope, because it's not. The neural network isn't executing really in the computer. It is basically its own VM. So as long as the class is compiled on a box and it does floating point math correctly.
The platform you're running the neural network on doesn't matter either.
No. Most of this code has only been run in Linux because I'm a Linux guy. So yeah. So
That kind of balances out the anti-Python thing there.
I owe people in this room beers. I feel great offense has been committed. I'm sorry. So, but yeah, it's literally just turning it into a secure lockbox. What you do with it once you get it out of the lockbox is up to you. So, do good. And scope, yes, sir. Yeah.
Yeah, so on the kind of adversarial reverse engineer side, I don't know all that much about neural networks. I know a lot about the learning. For creating fitness, is there a way to do it for the network itself versus the output? In which case, creating a fitness function that says make one monolithic function so it breaks diagraphically, is that a possibility?
It is a possibility. It would be really hard to pull that off. Giving it the inputs. If you could give me, I'm not an RE. If you could give me if we could sit down with Frosty Beer and kind of go over what that would look like in IDA Pro, how we could feed that as an input into the system, we could probably automate that. But again, whether it becomes computationally feasible, that's a whole other question. So, anyone else? Everyone's getting hungry? Okay. With that, thank you so much for coming out. So,
Thanks, Drew. Great talk, man.